Hello and welcome again to the session on advanced modulation techniques for high performance computing optical interconnects. In last episode, we read about the abstract portion, and this is the second one. So we begin the second episode from the introduction session, and it goes like this. Introduction. Optics are currently used in rack-to-rack interconnects for high-performance computing systems. Here, what does it means by rack-to-rack? Because in a data center, there are different racks. In that, we have transceivers. We have transceiver in the racks. So there is a communication between one rack to another rack through this fiber. So that is called rack-to-rack connection. So in the rack, lot of modulators, demodulators, or transceiver basically circuits are there, and it becomes very high computing machine, which stores data as well as do the computation. State-of-art rack-to-rack supercomputers interconnects are electronically very large-scale integration, CMOS switch fabrics for packet switching, and active optical cables for transmission. So there are two things. These systems which are there, they are basically very high, large-scale integrated circuits, fabrics, and it is used for packet switching. It is basically for networking purpose, computer networking. So in that we know different kinds of switching, packet switching, circuit switching, as well as message switching. So out of that, packet switching is used for the digital communication, which is advanced version. And other type of communication is that where these transceivers are used in active optical cables for transmission. So there is a fiber cable through which transmission takes place. The latter are based on vertical cavity surface emitting laser diodes, multi-mode fibers, and intensity modulation direct detection scheme. Later on means the communication which is taking place through the fiber. This is we have a transmitter, we have a receiver, and these transmitter and receivers are connected through the fiber. And generally these happen to be very long transmission relatively. So it uses your kind of vertical cavity surface emitting laser diode. This is nothing but a laser diode, but a sophisticated laser diode. Working principle is vertical cavity surface emitter. Multi-mode fibers, and the modulation scheme is basic, primitive one, that is intensity modulation. And detection scheme is the direct detection. Now, advanced modulation formats have been proposed for increasing the capacity of point-to-point link in next generation optical interconnect. Now, see there the reference number 327. Some advanced modulation formats have been developed for high data rate transmission purpose or high capacity or increasing the capacity. We go for the high modulation format or advanced modulation format. So why we go for simple modulation format or primitive modulation format to advanced modulation format? To meet the bandwidth or high data rate demands, because we need the transmission of data very quick as well as very high, rich in the quantity wise, like video transmission. Video transmission requires higher modulation formats because a lot of informations are there, as well as in a video we have a sound also. So that is why. Nevertheless, their deployment in the future data center optical interconnects will mainly depend on the dramatic reduction of system complexity. In the more distance feature, just-in-time optical packet switching might be performed using semiconductor optical amplifier as an on-off gates. Now, this reference number 8 to 10 are talking about this Optical packet switching. Now, this electronics engineer or communication engineers or network engineers are familiar with the packet switching and how to realize this packet switching in electronic domain they are aware. But in now people are working towards optical packet switching, which can be implemented using semiconductor optical amplifier. And references are given in 8 to 10. For instance, several optical interconnects based on semiconductor optical amplifiers have already been demonstrated in 8, then 11, 12, and 13. So optical interconnect where semiconductor optical amplifier have been used, that has been demonstrated. Now, representative examples of are data vortex. Now it is given in for reference number 14 and 15. So these references are given at the end of this article. We can see like 14, 15, what are those? So I'm going down to reference section of this article. We can see here 14, 15. Suppose this 14 number is this one. So the title of the article is the data vortex optical packet switched interconnection network. So this was published in IEEE Journal of Lightwave Technology, volume number 26, issue number 13. Pages are from 1777 to 1789, and it was published in July issue 2008. So here we can see optical packet switching networks have been implemented. And in 15 also, an experimental validation of a wavelength stripped packet switched optical interconnection network. It was published in 2009, April 2009, of the same journal, that is Journal of Lightwave Technology. So this is how we can go through. If we download these two articles, then we come to know how they have implemented. Although these two papers have been introduced in the introduction section of this article as a literature survey. So we should be aware about what is the state of art in this field. So now moving coming back to again this one, an optical shared memory supercomputer interconnect, that is called osmosis, which is given in the 16 switch fabric architecture. So from here you can see whenever we are writing introduction section of any article, we have to consult lot of already published research article in the area in which we are working, in which we are interested to work or already got the some result. So we have to apprise the readers that see these are the already published work which falls in our category or the area. Now next is the osmosis project 16 originally proposed a bufferless crossbar optical switch fabric implemented using a broadcast and select network architecture with fixed wavelength transmitters and discretely tunable receiver. So they are going a little bit into detail as far as paper number 16 is concerned. That is the osmosis. Osmosis full form is optical shared memory supercomputer interconnect system. So in this bufferless crossbar optical switch fabrics implemented using broadcast and select architecture. This is a network architecture. The name of network architecture is here, broadcast and select. Now question arises, what is this broadcast and select network? For that purpose, we need to read this article number 16. Then we come to know what actually this broadcast and select network is. Moving further, in the previous architecture, each receiver card used a semiconductor optical amplifier based two-stage wavelength selector to perform switching. So in the earlier article, this was the technology behind this architecture. In a subsequent study, we proposed the substitution of the original two-stage wavelength selectors by multi-stage wavelength selector. Now, this is the improvement. This is the advancement in the technology. Earlier, they have used two-stage. Now they are using multi-stage wavelength selector, exploiting the cyclic properties of arrays, waveguide, multiplexer, demultiplexer to reduce the number of on-off gates to minimum. So now these works have been reported in the article number 17, 18, these two. So what is the upgradation or what is the development in this work? In this work, development is that two-stage wave, instead of using two-stage wavelength selector, they have gone for multi-stage. And what is the reason? What is the secret behind this development? That is the cyclic properties of arrayed waveguide, multiplexer, demultiplexer. So this is again a structure, a very beautiful structure for array, which is called arrayed waveguide, AWG, and it works as a multiplexer and demultiplexer. And what is its application? Ultimately, the use of AWG waveguides reduces the number of on-off gates. Now, further moving, in the latter architecture, semiconductor optical amplifier concatenation results in the accumulation of amplified spontaneous emission noise and most importantly in distortion due to non-linear effect, especially self-gain and cross-gain modulation. Now in article 19 and 20 they have highlighted if we excessively use semiconductor optical amplifier one after another in a concatenated way. So what happened? Semiconductor optical amplifier will amplify the signal, but on the other hand, it generates also amplified spontaneous emission, that is the noise. And this increase in the noise will further lead to non-linear effects, that is called self-gain and cross-phase modulation. That is self-phase modulation and cross-gain modulation. So noise as well as distortion. And you can ask why this non-linear effect? Because if signals are increasing, signals strength or say amplitude or power is increasing, then the amplifier's characteristics is no more linear. It starts behaving non-linear, and this non-linear leads to transfer the power from one signal to another signal, or new signals are generated. So that is how this undesirable effects occurs in excess use of optical semiconductor optical amplifier. But this semiconductor optical amplifier happened to be used for network purpose as a part of gate. That was the compulsion. But excessive use of these devices will further increase the spontaneous emission noise, that is amplified spontaneous emission noise, ASE, as well as some cross phase modulation or self phase modulation. Here it is gain, self gain and cross gain modulation. Sorry. Now moving to next. These effects limits the maximum number of channel selection stages on the receiver cards and eventually the size of the optical interconnect. So this is how, these are the limiting factor. We cannot exponentially increase the number of switches in a limited space. The use of advanced modulation formats such as return to zero, that is RZ, differential phase shift key, DPSK, which is given in 21 and 21 to 24 number of articles. RZ, differential quadrature phase shift key, is here. This one differential phase shift key, this is differential quadrature phase shift key, which is given in 20. Then again, polarization shift key, 25. The polarization bit interleaved, RZ, that is return to zero, differential quadrature phase shift key. Another polarization division multiplexed quadrature phase shift key. In this, multiplexing as well as advanced modulation format have been used, which is given in 26 and 27, has been proposed to mitigate non-linear effect. So these are the some approaches through which we can decrease, we can minimize, or we can tackle the non-linear effects, such as cross-gain modulation in semiconductor optical amplifier. Now here semiconductor optical amplifier have been used for switching, but not only it is working as an on-off switch, but also amplifying the signal. And that too much amplification leads to non-linear effect. But now if we use this advanced modulation formats with particular line coding, then we can minimize this non-linear effect. This is what it is trying to tell. Nevertheless, different non-linear effects induced by semiconductor optical amplifier cross-phase modulation are pronounced in that case. Now 28 to 23, whatever we are doing, still this cross-phase modulation which I was talking here is still is more. Now in 10, reference number 10, we compared the performance of two versions of 64 cross 64 osmosis wavelength space switch fabric. The one originally proposed is 16, and its optimized version in terms of active component count proposed 17 and 18. Assuming 10 Gbps intensity modulation direct induction link. In a different study, that is in 26, we explored the use of coherent polarization division multiplex quadrature phase shift kit, that is PDM QPSK, to reduce the impact of transmission effects in the aforementioned optical switch fabric. So now see, the authors seems they are very experienced. They have already worked a lot in that field and they have published a lot of work. That is why they are citing here. Unfortunately, in this work, study experimental results suffered from severe phase noise limitation due to the broad 3 dB line width, that is 20 megahertz of the transmitter laser diode available in our lab. So they have used a what is called laser diode having 3 dB line width is equal to 20 megahertz. So this 20 megahertz in their term is relatively more. Now what they are doing, they have already pointed out what were the limitations in our earlier published work. Now in this paper we study for the first time the transmission performance of multi-level spectrally efficient modulation formats. Spectrally efficient means within the same frequency width, lot of signal points are there. Spectrally efficient modulation formats in cell switching interconnects architectures that employ combination of AWG and SOA, means this arrayed waveguides and semiconductor optical amplifier with different wavelength load per semiconductor optical amplifier. Moreover, critical issues such as cost, energy, efficiency, forward error correction, and latency are discussed. So these are the reporting item as far as this paper is concerned in a gist. So they actually they have already reported the result in the abstract, but now further they are telling that further they are adding some more information so far as this paper is concerned. So before moving, let us have a break. We will soon meet again. Thank you so much for attending this session.